We move on to the last talk of today. And we have Luca Scala, who's going to tell us about alpha prime corrections from Maxwell infinity deformations.
Thank you. Thank you for the nice introduction. So today we'll present you some research we are currently conducting in our university with our research group. And especially the last part of this talk will be based on joint work we are currently doing with Farcaster. So before I start, let me thank the organizer for giving me this chance, the Calista Construction for providing funding for me here, and Parita for introducing all this kind of double field theory and generalized version of their own kind of formalism I will not have time to tell about, but it's a nice introduction to everything I will say today. So let's start. Our aim is to find a nice way to compute alpha prime correction, a more convenient way than the classical way. Because the idea is that, as you all know, in string theory, usually we work at a low energy effective level, and then we correct this low energy picture, adding some tower of alpha prime correction. This is essentially an expansion in alpha prime, and to this alpha prime correction there corresponds higher derivatives, and then you can account for gravitational corrections like Riemann square terms and things like this. But these corrections are extremely difficult to compute because in order to do them classically you have to the usual way in which you do this is to look at scattering amplitude, and we had a nice talk about scattering amplitude yesterday. So and these are very cumbersome calculations, and only the first few orders are known. So the question is it possible to simplify this computation finding some underlying structure? So let's review the starting, the way in which usually we find this corrections. So usually one starts like considering, one can consider all the possible kind of corrections that are compatible with symmetries of string theories. But symmetries of string theory do not fix the coefficients of these corrections. And therefore, at some point, you have to match these corrections, all these terms, with calculation from string amplitudes in order to fix all these corrections. And you can see here that when you go higher in this in alpha prime, the number of correction becomes unmanageable. So it's and there is no apparent underlying structure to find out them. So it's a very complicated matter. So the question is there a way to reduce these numbers and this computational complexity, unveiling some hidden structure in the organization of these corrections? So there were over the time few various proposals. One we like a lot is this generalized version of the row. And this picture relies on an infinite expansion of the generalized tangent space. So because this builds on top of generalized geometry. It has a nice feature, so it reduces the number of parameters to just two, this A and B Parita was showing. But there is a major drawback. So this thing here works. Okay, this thing here works well till the second order. The pointer is not. Okay. Furthermore, the math behind it is not completely clear, and at some point is a little bit shaky. And higher orders were just conjectured. And furthermore, there is apparently no room for zeta-3 kind of corrections or higher kind of correction. And this is a nice no-go theorem stated by Siakamal and Linus in this year that applies also to this formalism. So very recently, based on some intuition of Daniel Butter, Achilles and Falk, developed a new formalism to try to formalize better this and generalize this kind of generalized version of the row mechanism, starting from the Polaczek-Stiegel framework of generalized geometry. The Polaczek-Stiegel framework essentially is a way to construct covariant torsion and curvature in generalized geometry, like extending the structure to something higher dimensional. And this applying this formalism to this problem of alpha prime So first of all, this method here relies on a much sounder mathematical foundations. So it has a clear structure given by generalized Cartan geometry, which I will mention in a moment, and on the concept of double cosets. And there is from here a well-defined procedure to find all the corrections stemming from the generalized Virchow-Dorot procedure. So you can find all this power stemming from these A and B parameters in generalized Virchow-Dorot. And I suggest you to go tomorrow to check Achilles' poster because he will show you how this works. But the questions are, there are still a couple of questions. First of all, can this account for zeta-3-like kind of corrections? And we would like to explore more mathematically how this deformation that allows us to consider this alpha prime correction works. So the rest of the talk will be based on these two. First of all, I will introduce the structure, and then I will show you how we are trying to solve these two last problems. So I mentioned that this thing here relies on generalized Cartan geometry. What is generalized Cartan geometry? So essentially, when you want to model in normal geometry, right? You have this kind of Cartan construction. So you can construct Cartan geometries as coset models. So you take some G and you model out by H. And for instance, projecting this to something well known, so the Cartan formation general relativity, it is that you take the Poincare group, you model out by the Lorentz group, and the thing you obtain is essentially the translational sector. These translation generators span the tangent space. And so from this you obtain the tangent space, and you obtain all the kind of physical quantities. So you obtain the Riemann tensor, the Ricci tensor, the Ricci scalar, and all your physical quantities. What is the analog in our framework? So in this kind of generalized geometry framework we are considering. So of course, since this is generalized geometry, we don't have anymore a simple tangent space. We have a generalized tangent space. It is a sum of tangent space and ecotangent space. And this notion here uplifts to generalized geometry as a double coset. So the idea is that instead of a single coset, now you have a group G, and you have to model out by the right and by the left by two subgroups of this G. But this does not explain to us which are these G and H we have to consider in our case. So now I will try to motivate what this question mark is for us. So a nice way to see this is to look at a notion called terreparallel complex. So there was something introduced by Martin Sedewall and Palmquist in 2023, and it was like a formalization of a terreparallel general relativity in terms of a complex. A complex essentially is just a graph made of whose vertices are vector spaces, and the arrows connecting them are have some particular properties. Essentially, they square, they are important. The square to 0, and the image of the first one is in the kernel of the second. So what is the idea here? So Martin and Falk were extending this notion to the case of generalized geometry. And in the case of generalized geometry, I will explain, I will now show you what this nice picture corresponds to. So let's start. So the idea is that in each one of these vector spaces, you have some geometrical quantities. Let's start for a reason that will be soon clear from this one here. These epsilon AB are the degrees of freedom of our theory. In this space, there live the generalized frame and the generalized filter. But as you know, these quantities here are gauge invariant under some transformations, some generalized gauge transformations. So for instance, let's take the B field that lives inside here. So transformations of the B fields are given by gauge transformations and generalized diffeomorphisms of the B field. So parameters of these two transformations can be combined in a single generalized gauge term CA. But this gauge parameter here has another gauge symmetry. So you have another gauge parameter here that generates this CA. And so this is how this complex working, where you have some gauge by a D, you generate another gauge, a bigger gauge. From this gauge, generalized gauge, with a D, you generate degrees of freedom. With a D, you generate your torsion and curvature. With D, you generate Bianchi identity for this, and Bianchi identity for Bianchi identity, and so on and so forth. Of course, the generalized frame is also invariant under local Lorentz transformation. This is very similar to how ordinary geometry works. So you need to introduce in this picture also this kind of Lorentz parameters. But when you apply a D to this thing here generates a spin connection, like in ordinary geometry. The difference with respect to ordinary geometry is that in generalized geometry, the torsion constraints, so setting T equal to 0, does not fix all the components of the spin connection. So you have some undefined components in this connection. Now, to fix this...
What the tilde signifies on top of the Young tableau?
This I will show you in a moment when I will explain what these Young tableaus are. Essentially, it means that these are traceless diagrams. But in a moment I will come to these Young tableaus. So yes, the idea is that there are some undetermined components in this spin connection, but you find that you can introduce some gauge parameters to gauge fix these undetermined things. Now, you introduce these gauge parameters, and these gauge parameters by a D generate some higher kind of connection. This is the well-known Polaschik-Siegel-Rho connection. And this generates curvature, Bianchi identity, etc. But again, all the components of the curvature, they are not fixed, so you have to introduce the connection, they are not fixed, so you have to introduce another gauge parameters, and so on and so forth. And this explains the well-known tensor hierarchy structure. So you have this gauge for gauge for gauge for gauge symmetry to infinity. Now, all this part here is fixed by this generalized Cartan theory. What about these additional gauge terms we were introducing? So it happens that since this is a complex, these tau maps here that essentially perform this local gauge transformation, they also have to square to 0. This means that all these diagonal lines, these diagonal red lines, are exact sequences. The thing that these are exact sequences means that you can study their cohomology, and via cohomology argument you can find the representation for this thing here. And here there is a little imprecision. So every time you see one of these diagrams, this is the box left times box right plus box right. So all these diagrams have a second copy because we have left and right sector of this generalized construction.
Wait, what did you mean by exact sequencing? Because they have no cohomology there. Exact means no cohomology.
Yeah, no. Yes, the idea is that. Yeah, you're right. You're right.
The truncated.
Yes. When you truncate them, yes, and then you find these additional terms via cohomology to make them exact.
I should not say exact. So there's only one exact, which is for reporting. This one is exact because it has previous cohomology. The other one. And you come over.
Okay, so. But okay, the idea is that via cohomology you can find all these terms here. But what is this structure here? What is this algebra we are finding? So let's take a quick detour. So you all know the Lorentz algebra, and you all know that Lorentz algebra can be extended to the Poincare algebra, adding translation generators. In 72, Schrader showed that you can take the Poincare algebra, adding commutator of translation with translation, and finding something that we call Maxwell 2 algebra. So adding essentially these 6 antisymmetric generators. And in 2010, Benares and Gomez showed that this thing here can be pushed to infinity. So you can continue adding commutator of translation with translation, etc., to find something that we call a Maxwell infinity algebra. And this thing here essentially is is a sort of extension by Lorentz by a Freely algebra generated by translations. Now in 2022, Dan Butter, in the Polaschik-Siegel formulation of supersymmetric double field theory, was this right-hand side here is the algebra I was telling you about, right? These positive level things. Introducing a Polaczek-Stiegel metric, he was dualizing this to negative levels. So PA is self-dual until the A becomes dual to the Lorentz generator, kappa tilde with kappa, L tilde with L. So you have this kind of extended Maxwell infinity. And he was noticing that if you take a subgroup of this algebra, so you mod out an ideal, the resulting structure, the negative part of the result is this resulting structure, we call it Poincare infinity, and we denote it as this for a reason that I will show you in a moment. So if you take the negative sector of this Poincare infinity, this gives the structure group of the Polaczek-Stiegel tangent space. So essentially, the idea is that you fix this positive part, because if you look at here, these representations here are now exactly the one I was writing here. So by tau square, you fix the positive part. By the Polaczek-Stiegel metric, by dualization, you define the negative one, and the negative one defines the structure group of this Polaczek-Stiegel tangent space. Now, it was not really working out till the end. It was just working out the first term. Now we have recently found a nice way to find all the projector for this Poincare infinity algebra. So we are able to do calculation with this. And the interesting thing is that coming back to the double coset model, the analog of this picture, and this is the reason because we call this Poincare infinity, is that you start from this Poincare infinity and then you mod out from left and from the right from the positive and the negative sector of this algebra. And the thing you're left with essentially are like double translation that span these double tangents. But so on and so forth, I was just presenting you the ordinary picture. Now we want to look at alpha prime deformation, right? Because this was the main goal. So how to incorporate alpha prime correction in this scheme? So based on intuition of Butter, Achilles and Falk in 2025, showed that you can start from a Polaczek-Stiegel formalism and deform the metric having here an ED invariant tensor kappa mini that encodes essentially the alpha prime expansion. And by means of generalized Cartan geometry, or if you want the Polaczek-Stiegel formalism, you can find the first correction in alpha prime to string theories. The problem is, what are all the admissible kappas you can put? So what are all the possible deformation of this model that you can capture? So how many of them there are? Because till now, they were showing that you can recover this generalized Birkhoff-de-Roo tower of correction. But for instance, what about zeta 3? Now, since I don't have a lot of time, I will present you a sketchy picture that will try to motivate you that in this framework, we can account also for a zeta 3 kind of corrections. And why is this so? First of all, okay, the sketchy picture relies on the fact that the possible deformation parameters in this model are given by the number of possible AD invariant terms in this K pairing. While the formal approach, of course, would be to look at formal deformation of this Poincare infinity and then check what happens. Now let's come to this sketchy picture. So the fundamental requirement, as I was telling you, is that this kappa mini is invariant under this non-positive sector of the Poincare infinity algebra. And by the way, when I use these Greek indices, these are like multi-indices that captures all the terms in this Poincare infinity that are not ODD terms. Essentially, the thing I'm doing is exactly here you have a generalized metric, Polaczek-Stiegel metric. This is ODD, and these are all the other indices in the Polaczek-Stiegel forms. Okay, so let's start from level 0. Level 0 is just Lorentz. So you take the pairing of Lorentz with Lorentz. What happens? Looking at, we know how to do representation of, we learned how to do representation of this Poincare infinity. And so we can look at representation of M. We can introduce, this is a symmetric product between representation of M with representation of M. And if you do this product, you obtain a dot and something else. And the dot, of course, is the AD invariant term in this thing here. So here we have a single dot, we have a single potential deformation parameter at level 0. Let's go higher. Let's consider level 1 generator, level -1 generator, so kappa. Pairing of kappa with kappa. Kappa, if you remember, has this traceless. Again, this tilde means that these diagrams here are traceless. Traceless hook times traceless hook gives a dot plus something else. So also here you have a single parameter deformation, a single deformation parameter. Now, for mixed level terms like m and k, where m is 0 and k is -1, this thing here is 0, and you can see this very easily looking at Young tableaus. Because the Young tableaus, one has odd number of boxes, the other one has even number of boxes, so the symmetric product does not give you anything meaningful. And so this statement is easily generalized to every pairing of an odd and an even level generator. So we can start to account for all these deformation parameter writing a matrix. So these are the level of the negative non-positive level algebra. And these are the number of these are the deformation parameters allowed by the pairing at that level. So m with m, just one allowed deformation. K with k, just one. All the odd with even gives 0. Let's go further. For non-diagonal terms, the situation becomes more interesting. Why? Let's consider the pairing of M and L. Now, M is just this two antisymmetric, while L has this structure. From this pairing, from this symmetric product, sure.
What is this circle dot?
Symmetric product.
Okay.
So of course, you just get one contribution here, one dot from this thing here times this thing here. And so you get, in principle, you say, okay, I should add another parameter delta to my family of possible parameters. But from AD invariance, you can write the following nice equation where these are elements in this non-positive Poincare infinity algebra. And why is this interesting? Let's look at this plane here, M with L, right? Now, the generator L can be expressed in terms of commutator of K with K. Then I can use this thing here and go to here, and K with M gives me just K. So this pairing here is proportional to this pairing here. This means that this new parameter delta is proportional to the parameter, it's linearly dependent on the parameter gamma we were finding before. So this is not really a new parameter, a new deformation parameter that can appear. Let's look at even higher orders. Here we have 4 boxes generators, so L generators with 4 boxes generators. Apparently here we have 3 invariant terms, because we have this thing here with this thing here gives 1, this thing here with this thing here gives 1, this thing here with this thing here gives 1. And we worked out all this calculation of mathematical. Here, let's consider a 3-box generator with a 5-box generator. So here you obtain terms only from these 2 traces part of this 5 boxes generator, because they are the only one that can pair with this. So here we have apparently 2 deformation, two invariant terms. Here, 2 against 6, you get 4 invariant terms. So 3, 2, 4. But what happens? I will briefly show you that these 3 parameters are again connected to these 2, and these 4 parameters are really connected to these 2. So the minimal number of real deformation on this of this tree stemming from this 3 contribution is 2, because the other one are linear dependent on these 2. And again, so this is 1. Here we identified what this with this, and now we just identified all this term here. Remember, here we have 3 deformation parameters, here 2, here 4, but the minimal number is 2, so everything should be dependent on this anti-diagonal by these 2 parameters. And so we just write on this diagonal that there are 2 deformation parameters, epsilon and beta. But still we have quite few deformation parameters going to a relatively small order. Is there a way to further constrain these parameters? And also another weird thing is that when you start with the deformation parameter here, you would expect going lower in levels this parameter to propagate. So this is like an alpha prime correction, this is an alpha prime square correction, alpha prime cube correction, and so on and so forth.
Got one more minute. So.
Oh, okay. Very quick. Yes. The point is that we were considering only the linear level, so underform commutator. But the kappa pairing introduced also some nonlinearity in things. So the commutators, the ordinary commutators are M with M give M, Lorentz with Lorentz give Lorentz, M with K give K. So L is a grading of the algebra. But when you introduce this kappa, there can be some terms that breaks this grading, and this commutator is modified. Since this commutator is modified, you can check that these gamma parameters of coming from the pairing of K with K is exactly alpha prime. And so at the end, you find this thing here. Now, this alpha parameter, alpha square, alpha cube that propagates, gives the AB deformation of general Berkshire of the row. Beta is a new parameter coming at this order that might account for zeta 3 terms, but comes to 6 boxes, so it's very complicated to do computations with. So to come to our conclusion, so this Polacek-Stiegel formalism based on generalized Cartesian geometry might be the key to better understand the structure of alpha prime corrections. The subalgebra of this extended Maxwell infinity, namely Poincare infinity, seems to play a central role in this. In particular, deformation of this algebra seems to clarify the formal structure between the Polacek-Stiegel approach to alpha prime corrections. Different families of deformations are we can find different families of deformations that might also accommodate for zeta 3 terms. Work in progress is to fully characterize all the allowed deformation, meaning all the allowed invariant kappa minis, and the corresponding algebra stemming from them. Show that zeta 3 is not only possible in this framework, but it's really there, so match the zeta 3 terms with literature. And then in the end, the dream is to write universal formulas for the possible alpha prime corrections in this framework. So that's it. Thanks you for your attention, and here's some bibliography if you're interested.
Okay, we have time for maybe one quick question. Okay, so maybe I can ask. So it seems quite miraculous that this would somehow have all the same information that T-duality does, right? You can fix these corrections also using T-duality. Or we believe anyway that you can fix the same information. So is there some argument why this Maxwell infinity algebra should contain the same information that T-duality does?
Well, because
you didn't put in strings anywhere, right?
Yes. No, see, yes, the idea is that essentially this is a sort of like higher order generalization of T-duality. So essentially you are introducing, it's like going from, like in T-duality you have like covariance under ODD, right? So you are, in this case, instead of ODD you have some infinite dimensional algebras, right? And the structure of this is like captured by this kind of Maxwell infinity, because this thing here contains also ODD in some sense. It's something like bigger. So the idea is that this works because, of course, then you can reduce everything to ordinary T-duality. The reason we are doing this kind of extension is because in this extended theory, we might hope to find also this kind of additional deformation parameter like zeta 3. As far as I understand, in ODD is not possible due to the no-go theorem you recently
right. It's connected to my question. It's not clear to me why it should be possible here if it's not possible in the generalized geometry.
We still have to check. So till now we just show that there is room for additional corrections, and they come at the right level in which they should appear in string theory. The thing is that now we are adding much more like physical parameters, and maybe it is possible that in this way you can uplift really this kind of filter definition you couldn't uplift to an ODD covariant theory. Okay, but this is still something that we have to check and better investigate. The idea is just that being something bigger and finding this correction exactly where they should be, there is the hope that maybe this bigger structure allows for more to capture also these additional things.
Thank you. So in the interest of time, I think we have to end there and say further questions. Just two quick announcements before we do that. Tomorrow, as I already said a number of times, the venue is different. 2 houses over, house 4. And for those of you who signed up for the dinner, we will meet outside the Nordica building at 5:15 and walk to the subway. Okay, but let's thank the last speaker of the day.